know that how can we run a CUDA code in the Colab. So Colab give a kind of cloud source where they can give you resource to certain GPUs. So once you open the any Google Colab page that I've shared with, you can go to the runtime. Click the runtime and change runtime time. So you have multiple options. If you have only use CPU, you can use GPU and you can use TPU. TPU is basically tensor processing unit. So we want to use GPU, so we select GPU and save it. Like when you are writing your own Colab, that's how you need to do. First, open a Colab page, go to your runtime system and select that you want to use GPU. Fine. So now we want to use some codes, like some installation need to be done to run the CUDA in the Colab. So these are the first of few of the libraries that is necessary to download the CUDA libraries and CUDA compilers. So this first two commands is basically doing that. So the link that you have got, you cannot edit it. Like you can edit, but you cannot save because this link is specifically written by me. So you cannot edit that. If you need to save anything, you have to make a copy of this particular script.
File, save copy details, right? You can do that.
That is your own copy, basically. When you can save, modify.
Click a file menu. In the file menu, you will have a save copy in the drive to do that. It will be one copy of it. This file will be saved.
So everyone is up to this. Everyone done this, right? So now first install this libraries. You just need to click this and it will run that particular command. It's pretty similar to Python. Python's Jupyter notebook, if you have worked with, it's like that. So it's installing. You are you have you logged in as well or signed in like here? You need to log in as well. Logged in, right? So installation is done. Now, what is NVCC plugin? This is the compiler, CUDA compiler. NVCC is the CUDA compiler. So we need to install that as well. So next, let us check that what are the NVCC version that we have installed, and NVIDIA SMI will give you the particular GPU code, GPU architecture that you have been assigned with from the Google Colab. So for me, it is NVIDIA SMI 525 and CUDA version is 12. GPU is Tesla T4. Everyone got the same GPU or there might be some difference because a lot of people are accessing this Tesla T4. Everyone got Tesla T4. So in case sometime you are using Colab, it may happen that you got some different GPU, not Tesla T4 or some older GPU, because this is they give free access for some time and after that it becomes paid. So every day there are certain access time and the newer GPU is like more expensive, and if sometime a lot of people are trying to access the same GPU, then they start giving older GPU versions to the free customers. So you sometimes need to check that if it is which version of which architecture you are assigned with. Because when you are compiling, sometimes you may need the extra flag if it's an older one. So next we will start with a simple vector addition code. So that is already taught by sir. So what does vector addition do? It is a long boundary array and it will two such vector is given and you need to add it one data point at a time. So if we are doing it serialized fashion, what we do is that we start a for loop from 0 to the number of elements. So suppose there are 100 elements. So it will add one by one. So 0th index, first index, second index, so on. So this is plain C program that everyone knows, very simple. And how we write the main function, we ask what is the number of elements, we're scanning the number of elements. Then how much memory we need for dynamically allocating the memory. We get the number of number of elements, the size of, if it's a float, it's float. If it is integer or double, it's depend on what program you are writing. So here we are allocating the space for vector A and vector B. So we have this much space in the CPU code. And also for the output, we need an equal size of vector in the CPU code. So all these HC means basically host A, host B, host C, kind of short form of that. And after that, we need to, this is basically like we need to populate that vector. For that, we can use a randomly generate those value, or we can have those data in some files. This is what we basically use in our day-to-day life. Like we have the inputs in some file, or you give the input, you type it. And I will give some other example where you can take the input from file as well. So this is like to check the vector addition. We just generate some random numbers within to populate this vector A and vector B. And then we call the vector add function. And within the vector add function, this HC is basically the output where it gets stored. And in this part of the code, we want to check that actually the vector addition has given a correct answer or not. So we are checking that absolute value of HA and HB and minus the whatever the output is HC is almost 0 or very close to 0, is because of how much precision is there. So depending on that, you can equals to 0 or something greater than like this. So and if it is done, it test passed, and after that we free this space. So this is a simple vector addition code. And before that, we have written something like this. So this is specifically for the collab thing. We need to mention the collab that we are, please create a file in the folder content and source with the file name vector add simple.c. This is basically, and with that, if we write this particular syntax, it means it will generate that file and keep it in that particular location. So if we think and while compiling, we just use GCC, and for collab, this is the command it takes, like an exclamatory marks. After that, whatever the compilation command we pass. So in the argument, we passed 1024 and it's pretty much done. So now we have this CUDA code. If we write like write exactly the same code, only we, instead of calling the CUDA, calling the vector addition from the CPU, we'll write a separate function, which is for computing the vector addition in the GPU. And correspondingly in the host code, there'll be some minor modification. So again, we are mentioning this particular syntax and telling the collab that this is a CUDA file. So we need to write this CUDA, and the file name is vector add simple.c. And these are some of the libraries. And if we compare to the simple serialized C code, the difference is that instead of a loop, we are saying that if this particular index is within this range, just add. Because a lot of threads are there, basically 1024 threads are there, and all the threads are identified with a unique index. And if that index is within that range, just add. And they're happening parallel. Okay. And in the main function, we again ask for the number of elements. And we generate the space in the CPU as well as GPU. Both we need. Because when we are populating, when we are reading from a file, from where will that file data will be written? It will be written in the CPU. But the computation is happening at GPU. So we again have to transfer this data to the GPU memory space. The computation will happen. And again, that computed value need to be copied back to the CPU, where you may need to write back into a file, or you may need to pass it to another program. So for that, we first allocate in the host space, same as the serialized code. And again, we initialize some random value for the vector A and vector B. Next, again, we have to generate space in the CUDA, in the GPU. So we used CUDA malloc, and we passed the size and the particular array pointer for both A, B, and C. And these are the commands to check that whatever command is passed for the CUDA particular function has written successfully or not. So it may happen there is not space. Suppose you allocated a lot of like 2 to the power 20 cross 2 to the power 20 matrix multiplication you want to do, and you wanted to CUDA malloc and that much value you passed, and you didn't know, you didn't add this code. Okay, so and suddenly you're seeing that the code is not running. So how to identify that? If you added those kind of error handling, then it will say that it would have given some commands errors that memory space is not available. So that much space is not there in the GPU. That is why you could not allocate that space. So this kind of error handling is necessary in GPU to decode, because unlike in C or other Python code, it's difficult to decode there, debug. So you are getting some error, or you are not, you are just checking it's ran and the result is not matching. So it might feel that the logic is implemented wrong. Again, you went back to the function, you modified the function, but you check that again it's not coming. But it's actually maybe that the space is not allocated, maybe the device that it's there, it's corrupted, or some kind of error has happened. So it's very necessary, especially in CUDA or GPU code you are writing, to do error handling. So every CUDA function that you are calling, like CUDA malloc or memory transfer from CPU to GPU, after every step you add some error handling. It's better to use some error handling code. This helps you to debug very fast. After that, again, we need to transfer the memory from CPU to GPU. So this code, CUDA mem copy, is basically transfer the data from the host A pointer to the device A pointer, and it's saying the size, how much memory it has to transfer. And this parameter, CUDA mem copy host to device, pretty like in English, it's almost written that copied from the host to the device memory. And again, we have the error handling part to check that it has happened or not, both for vector A and vector B. And then we have to basically start the kernel or that function in the GPU. That's the CUDA kernel. So we need to know that what is the block size and thread size that we want to launch. Suppose we restricted here, we have just hard coded, say 256. We can change it to 1024 as well. So if it is 256, we know the number of elements, how many number of elements is there, and from there we calculate the number of grids. And we know that it's a 1D array because it's a vector. So it's preferred that we will launch in a 1D fashion only instead of 2D fashion. That will make it more complex and doesn't make any sense. So we have this vector add. So we first calculate the thread per blocks and block per grid, and we launch it that launch the vector add function with the parameters DA, DB, DC. These are the pointers for the device vectors and the number of elements to be processed. And what is the block size and thread size? That's written here within a 3 angular bracket. This is the format that we do to launch a CUDA function. So if you compare this along with the function called in normal C code, is basically just this. So in between this, we are passing the vector, grid size and the thread size. That's the only difference. Okay. So once that is done, we have to again check that the actual computation has been finished or not. We have an error handling part. And once that is done, we copy back the memory from the device to the host and we compare if that is actually computed correctly or not. So this is where we do that logical implementation is correct or not. So it's difficult to write a CUDA kernel code because the logic is not exactly how we're used to think. Like we have some serialized way of thinking. That's how we have been trained to do for a long time. So thinking in a parallel fashion is difficult and often the implementation logic gets wrong. So it's better like when you are writing a CUDA code, at the end you cross-check that it's actually getting the answer that you want to reach. By computing your serialized code, the answer is matching in both. So if the answer is matching in both, that means the logic is correct. And if it is not matching, then have to check that if all the error handling code is correct or not. They have reached that particular steps. All the steps have actually reached successfully and not. And then that means some logic is need to be changed. So this is how we debug. And just like in the C, we free that space. Here also we need to CUDA free the device space. So they have a limitation how much memory any architecture we have to check that as well. So we have written it for, now we have to compile it. So it's just like GCC, we have to write NVCC, the code location, and the output is the executable level, just like GCC. So we compile. Now this is generated. So this is what I was saying, that you have to check the architecture. If you are assigned with the older architecture or something, you can check this link. So this link will give you the exact flag variable that you have to use. Like in some older one, you may need to specify the architecture that you are receiving. So there. So if here is a list, you can know that what GPU you got. From here, you can get the flag and that you need to pass. In case you are writing a big code and you are not receiving that particular GPU architecture, then this might require at some point of your programming. So let's run this one. We passes 1024, so the test has passed. So this is like whatever is taught in the theory class is almost as just iterating line by line in a way, and you have it in your hand. You can like play with it. So we'll give a small assignment after some time. If you have this code, you can very easily write that code as well. So next, if you want to check how the computation is happening, so like how faster is it, we need to profile them, right? So each of these functions, how much time it is taking. So for that, they have a profiler called NVProf. So this will profile how much time will take at each step. So if we run a NVProf, you can see that how much GPU activities has happened. Each of the API calls, how much time it has taken. It's a very details will be given. Like if you see the vector addition has actually taken only 4.7 microseconds. And that host to device and device to host, it took averagely 1.9 microsecond. Whereas CUDA malloc, CUDA reset, these take in the second of milliseconds. So it takes a lot of time. So when you're optimizing a particular GPU code, you can profile and check that where the time is going. Like, is it in the computation, it's taking a lot of time, or is it the data transfer is taking time? So you can identify the bottleneck, and based on that, you can modify and optimize your code better and better. So up to this, if I say that from here, can you write a vector multiplication code like Hadamard multiplication, which is basically here we are multiplying one vector with another vector at each index, like AI will be added with BI. If we just say that Hadamard multiplication is basically AI cross BI, can you write the code of that Hadamard multiplication? Just try. You can copy paste from this code only and check if you're able to write, compile, and finally execute. We'll give like 5-10 minutes. Yeah.
And I have a question like that. If I have a conversion simulation or a fluid dynamics problem, like this is load is my fluid domain, and I want to compute the velocity at each point inside the node. So then I don't have any prescription of the what value should I will be getting. So then how will I test my
Questions? Like I want you to be like update to up to this point that you are able to code and that. Then we will specifically point out to this problem and check how we can parallelize it, write it in CUDA code, how to apply that problem. So we'll go to that point.
There is a problem.
Next.
No.
Is it too much like to write tailing to code after some half an hour? You can try like we have given all the resources. Just try it.
What is
So once you put is a too big number, you can start with a small one, say only a 32 size vector. Start with a very small value. So that's what we have done in the scene.
Wait. Here it's run anywhere. No, I will maintain another copy. Somehow got the logic out, but let me run it. So two main sections you are seeing. Section to What is the Hadamard product? What is that Hadamard? Specification. Hadamard product. So you make this a scale and this is a matrix. Like we have to program it. Just seriously the what's the word?
For the 56 threads will be in one block. So now we can have it's only a 32 vector size. What block size and the thread size.
Very, yeah. No idea.
This was the section how it's for 32 vector, what will be the parameters. Actually, no one is writing anything or executing. Everyone has like compiled and run, right? Every cells that after which we have covered.
Right now,
Vector
Instead of 256, we have 32, no?
Yes.
First question mark will be 1, second will be 32.
Yeah, that's it. So if we make it
32 by 32, like divide. Yeah, divide.
yes. So if we say we change the size to 2 to the power 20, 1048576. So the same formula.
No, what you were saying, like 1026, you want to make 2 power something.
So vector size is now changed to now. So now instead of that, we changed it from 2 to the power 20, which is 104576. Something like that. And your block size was still 56, it was 256. So it's divided by that.
16. Oh, yeah. 2 power 10 divided.
Suppose your block size, so more number of blocks need to be launched. But in per block, you have the capacity of 1024. So you're losing parallelism there. So we should occupy as many threads as possible. So it's better to launch 102 threads, 1024 threads per block. And 2 to the power 20 by 2 to the power 1024 is the number of blocks. So this is the important point where when you are coding to identify exactly what should be the launch parameters so that the GPU is used to its maximum capacity. Shall we give a little more difficult question from there where you have to actually write the code in the Hadamard multiplication? All you need to do is instead of the plus sign, you have to modify it to multiplication. Pretty much same. So suppose this vector addition is there. Whatever the output of the vector add will be multiplied with a new. So vector add is given in the code, and now we have already the vector Hadamard. This part is also, this code is also with you. You have to join it. Basically, its output will come as an input to this one. So now we have to write a new host code where
Input as vector size for me.
same, find the same. Suppose so if this vector addition is there, its output is C. This goes to suppose square root or square root. Okay. So whatever the output of the C is, at every index it will need its square root value. And that will give our output as D. So now we have to write a new kernel itself. And in the host code, we have to modify, like after the vector addition, that need to come to host and again host to device, they have to be transferred to device, all that particular kernel code, and then again read it back from there and get the output.
There are two kernels. First kernel is your vector add, which adds to vectors and produce the result C. And second kernel should take that C, which is produced by vector add, and like the square root of every element. Okay, so you should have two kernels. First kernel is vector add, which is already with you. Right, another kernel, which will take another vector as input and produce an output, which is square root of every element of that.
So please write that code, then you will definitely face problem. You will raise your hand, then we'll go and try to solve that. That is the point of giving this assignment.
To change this one, right? Come down. And from this location, it says I have said it is the come down, come down. Come down. पहले ये हमारा And I see this is the output that is while returning. Should we run again? Wait, actually, the person of one. This warning is a.
See, in this case, in case of vector and no, what we are doing is first we are trying to identify index of a thread, calculate index of a data element on which the thread is going to operate. So this statement will remain same. Only thing will change is this one. So we'll get d of I is equal to sqrt of c of I. The parameters that function will take will be different because that function is taking only one parameter, which is your c. Okay. Okay, so that will be constant float c, and result you need to store somewhere. So constant float star d, comma number of elements. Okay. So that will be the definition of that function. And then underscore global mode of the function. Okay. And you will call this particular function after the first kernel completes the execution. Within it will be sections. Kernel should produce vector addition. Subsequently, you want square. Okay. So first this kernel need to be finishes execution, then only you will launch this kernel.
We are writing vector add as one function, like
Yes.
after the whole result, we are generating C result, like
Yeah.
C, which is like vector add. So when we are doing square, one method with search, and you told that in the same block we can write D equal to sqrt of C, and in that we can write float star D, and like null everywhere we'll incorporate.
Right.
But will it be better if we can write another void like square root something and then writing like
Yeah.
float star C, float star D?
Right after this, you just do a
Yes,
square.
new function we have to like call, and then we will write in that.
So this is only for an assignment. Like when you are doing a code, it's definitely like if it's happening one after another, anyway, you have to call multiple kernels one after another. It's better to merge them in one single kernel. So that is one kind of optimizations that are taught in the class. Like when there are multiple kernels and the operations inside are actually happening one after another, there is some kind of synchronization needed required between them. It's often happened that they are merged together. They are called kernel fusion.
It's in same block, like
We
what
can,
the code
yes,
saying,
that's can be done. So this is for just assignment purpose. Like you have the vector addition code, so you write a small, we want to write you one new kernel and write the corresponding host code inside. Just to get the feel of how to write, like from my experience that we only learn how to write any programming language when we start getting errors and try debugging it.
You see the output of that, and then just there was one that the collaboration. Yes, it's yes, it's going for the brands of engineering itself. Right.
Shall I start writing or wait a bit?
Yes, continue. Yes, I start writing.
Only the present here is symbol will come. Here symbol will come. The present then it's like a good bad and all. You want to use everything in runtime. Yeah. Application visibility like this. Now something is there, file is written to get that. You don't have to report or something. If we click, this is the output now. You have seen that file, that feed of this one. This is the file. It was not showing.
This will come. We are planning to this already. Here instead of T equals to T, I square Exactly. So that's your connectivity. Let's give your this there.
So we are giving this land is giving this place the writing like
So here you bring in space for B. Define our identity and it takes create voting post and
once you yes. Yeah. File is written somewhere, but
so your input will be float C
okay.
and your output will be float D.
See, it would want to
The kernel will be pretty much this, right?
yeah.
C is coming, D is coming, here DI will be square root of that. So in the post code, where are the additions that we need to make? So in the vector code, where is the first point where we need to modify? In the host code, what are the new modifications that we need to do?
This is the high mark product.
No, this is the joint of this one.
Co-join.
kernel 1 followed by kernel 2.
Okay.
So we have a new vector D. So we have to
Define it.
allocate space because
Square, yes.
no, how will you call that? In the host, you have just you're able to call the get tags.
But in the device side, I can see that. It looks as part of that. I will have to
But you have to allocate the space for this. Yes, like how do you processing that ultimately your data is correct or not. Your output is in the device, but from there, if you want to do anything with that data, suppose you want to store it in a file.
Or split in the C. And the panel is the C. That's when.
So again, let's copy that memory from C itself again.
What is saying? Sense. Operating of C.
Right, what is-
Operating of C already at the time. It's the island doesn't like. The box I think is not related to device.
People might be difficult to understand.
This thinking of optimizing.
Yeah.
So,
So we can copy this line.
and then. So you're performing both the
And in the error also, we can check that HD is actually allocated or not.
So are we performing both the codes in the same kernel itself? That's what we
Sorry?
are we performing the same? Oh, okay. Got it. Mixed with the
So you can say the whatever doubt you had, because then others might are getting the same doubt. That will be.
yeah. Now I got it first. You were trying to add it, and after that you are going to square root it. So the
Yes.
same code has been done in the same kernel itself.
Yes,
Great.
yes. So no need to initialize again because it's already
Already.
used for the vector addition. Output will be
The
the input.
We print that.
So DB is created, DC is created. Again, we have to allocate vector for D. We allocated the space for D as well. This is fine. A is needs to be transferred to B. A to host to device. B is for B as well from host to device. But for C, we do not need. C is getting computed there itself. So here vector addition is called. The device is copied back. So now we have this DC. So again, we have to transfer it back to.
Sorry. Here we go.
So we, you might feel that we have this DC again. We have to transfer the memory of the C from host to device. That is not required because it's already there. It's computed and the memory is there already. So right now, HC is both in device and host. So if you want to call, we can directly call next one. So instead of add, we have to write square root. Instead of DC, we have E. Cross check if there is any error or not. So now we have the computation done. Then we have taken copy the device back to this. So once this computation is done, we have to copy the D from there. D Up to this, is that clear that what modifications we did? Those are the points where we need to add when we're writing anything else. So finally, in the verify, what we will write? HT minus what? This, right? The output of is in the D and square root of the C, they should be equal. Fine, right? And we also has to free the DD as well. And since we used square root, we have to add the library math.h there. Let's compile. This is basically writing the file. Next, we have to compile. Let's see if we did any error or not. There is an error. In line number 177, it must be integral and unscoped now. 77.
Actually, what does the line mean after verification? Like verifies function, right? The line fabs ht minus.
Bracket is fine. Is there? There must be before 177. Let's go back to that. Or
Especially
bracket.
But what about the other function? You need to first add and then put to see.
Is it? Remember, they can square with the function.
SQRT is only on
Vector add, vector SQRT.
capitals. Which are capital and which capital?
Like the one.
Which is
Others are getting the same edit or getting compiled.
We haven't tried that.
Edit the changes, those changes.
I don't know the code in the verify. You use fab d minus the square root of c, and it's greater than 1e minus 5. I don't understand.
Okay,
Or-
this line, this is basically checking that the difference between the output and the serialized square root function is equals to 0 or not. So, but in float, you cannot compare with directly equals to 0 because of precision. So you are saying that if it is greater than 0.00001, then that's a wrong value.
Actually, verify. Okay, okay, okay.
Okay, so the error was very simple. Here I was not given. It was HD minus this working. So the index was not given. That's why it was giving the error. So now you compile and we explore. So they have passed the test. Did you follow the same step and do it in your machine as well? Like whatever steps that I added, did you do that or it's running fine,
So
right?
it's taking time. It's
Acha.
no, it's compiled. It's updating. Like it will take time.
Okay. If it takes more than 1 minute, then please test because that's not the problem.
See, we can't even use this chair and get us right. Yeah. So let's try. So let's try what he's trying to basically we have to given the code of addition. So A plus B we get to C. C stores the value page of B. After that she is doing square root of C and the value is A. So it's initialize. So we have to initialize the variables and allot the memory space to it. And after that we have to verify whether B minus square root of I is between them is less than 0.00.
How to modify the rules. That's what I'm saying. How you can so let's do that. Technical and that reduces your
Yes. You are trying to create the same thing, right?
Yes.
But can we add in this?
Remove the constant. Constant will be created in error.
So should we put in our sorry.
That itself.
Sorry. So now can't we add it in add init itself?
Yes, yes. It is just an assignment to like make you realize how to modify the host.
I don't know this bold code, but I get the idea how it.
Yes, that is how it is.
So I'm when
Yes.
you ask me like that, I
Yes, yes.
So,
അങ്ങനെ ഇനി നെക്സ്റ്റ് പറയുമ്പോൾ നമുക്ക് ഡിഗ്രി അലോക്കേറ്റ് ചെയ്യണം. ഇതാണ് നമ്മൾ ഈ അലോക്കേറ്റ് ചെയ്യണമെന്നുണ്ടെങ്കിൽ ഇതൊക്കെ ക്രിയേറ്റ് ചെയ്തില്ല. So we have to just create an another variable just like this. Just replica. Therefore, we will create this HT and we will क्या करेंगे थोड़ा सा कर देंगे. ठीक है बाय ठीक है ये should be yeah, I'm feeling the pain when you felt the morning. But FDS door, you have spent. Or sleep, or just lie down. My mind is कुछ भी नहीं कर सकता. I can reach absolutely fine. This one.
From the online participants, if anyone have any problem, please raise your hand or you can post your queries in the chat or questions also.
Is it run successfully, but how can I see the output? It shows it's run.
It's compiled, you haven't executed.
Okay.
This is your execution code, like dot slash how it's executed. That is your execution. Yes.
After changing the output will come here.
Result verification failed at elements. Result verification failed at. Did you verification?
Yeah, I had done right. Like
but it didn't match. So there is some error. Execute, not compilation error. Compilation is done.
okay, so execution.
Yes, and it's at the data point itself.
And the main thing is that like I didn't submit the previous class like get drawn for particular and that is 56 पता नहीं चला एक overview outline मिलेगा क्या like
So yes, if it's online, you will definitely get a lot of resources. So basically, how just the way in C, the memories are like contiguous memory we have in the stack
yeah
or whenever you. But when we are thinking in a structured fashion, when we are thinking of multi-array, we are thinking logical. That this is how the memories are. But in the actual memory, they are contiguous. That's not how they are like structured like this. Here as well, in there the threads are all like one after another like that.
yeah
But we are trying to think, suppose handling a 2D array, it is difficult to write a code thinking it in a 1D fashion. Just that we think it in a structured way 2D array, 2D thing.
Yeah.
Here as well, like here the threads are arranged like that. It's not about the memory. Here the threads are arranged like that. Each thread is if arranged like that, then this thread point will exactly work on that data point. Suppose
Each what the
the threads will work on a 2D array. So here, like if it's AI and BI, the operation is one
one of
addition.
done, yeah.
Okay, and that is done by one thread.
Okay.
And each thread is working on that particular memory. So memory address is also I for both, and the thread location is also I.
Okay.
So there is an alignment. You do not have to think exactly and think of it in 2D. It's a 2D matrix thing. Okay. And there also you are doing some multiplication. So if the threads are also aligned in a 2D fashion, all the threads are in a 2D fashion. Okay. And the data are also 2D. So now your operation is much easier.
Yeah. Yes.
Otherwise, you have to think like this thread is doing on which data point and that data point. The next thread, then you have it's difficult. It's not impossible. That's actually internally that are done.
Yeah, just it's doing like the zeroth array is adding itself like A array and B array are adding.
Addition is also doing the zeroth thread.
Yeah. But why did we change like 132 and 32 one? What has been like adding for? No, you said to change the block from 256 to 32, and it says one.
That is to check if your understanding is clear or not. So in per block, there is a limitation how many threads it can run.
Okay.
And there is a limitation how many threads can run in one shift vessel. So if your program needs such an its size you know,
Yeah.
and you also know the architecture specifically how many threads they allow per block. So then you have to define how many blocks it has to launch.
You are saying that like if it is a big number, then our memory will be filled, so there won't be space to run it.
It's serialized. So for one node, the whole thing is done, and again the next node, the whole thing is done, and then done.
Then just so just you are changing the number of blocks.
Just number of blocks. Suppose that question is 34, right? So your block give you the opportunity to do 1024 threads together. 1024 threads can run parallelly.
Okay.
But instead of using that, you're only using 32. So for that, your number of blocks are also increased. So you launch more number of blocks. But in every blocks, almost 80% of the threads are doing nothing.
Yeah.
So you are basically not using it, utilizing the resource correctly.
I'm getting confused. Like, what is the block referred to? Is it the storage of actually by the array? What I said, like A of I and B of I, you said. I get it like it's an array storage, and I thought you were referring to that it was a block, physically a block.
No, threads and blocks are like a lot of threads are there in thousands of threads are there. We then usually make it some kind of unit. Suppose then we are making it as how that many threads is difficult to handle. So then we segregate into certain number of blocks. Like let us focus on each block. In each block, everything is happening the same thing. And such a block can happen multiple times. So when for a block, they have some shared memory. So these are more optimizing things. So this particular block have some memories that are shared among all these threads. They are not shared with the next block.
Yeah.
Because their architecture is like there was that SPs, BSP. In the first slides, sir was saying SMs and SPs. So it's basically at that level that the SMs has a common memory space, so all the threads had access to that particular common shared memory.
Maybe my view is wrong or maybe correct, I don't know. Right? I'm getting the view is like I'm comparing it with the APS. Like there are many there are many data I want to calculate, and it's a single operation. It's A plus B. So there are many processors. So I am just giving each processor the work.
The data.
Yeah, data. So A plus B will be done in this one and by the zeroth array, and the second process is one first array, which is the second array, and it goes in.
This part, but I'm getting some error at 160.
You want to come here?
No, ma'am, I will ask you after.
That one way, and don't confuse with the array memory thing. These are threads. These are processors. These are CPU.
Okay, what I was asking, like, each thread, which means it's like
Each thread is working on each.
just a second. I'm looking.
I request all the participants to open the second OLED file, which is for matrix multiplication. So let us start. Let's start and see how.
Has everybody opened the second collaboratory? We will be starting with the matrix multiplication. I hope everybody was able to follow the first vector multiplication and the assignment. You can try it yourself. The collab file has been made a copy in your own drive. So we'll be starting with the matrix multiplication now.
So second thing is like one different for this particular program. It's like the data space. Data space is two-dimensional. So vector program, we have one-dimensional data, and you have not with one-dimensional grid space. In this particular case, we have many operations to be performed on matrices, since metrics are to be data. So we need to take into account that dimensional space launch. In this particular case, what we do is, so this is a simple program, matrix multiplication. We try to understand the basics of that, and we try to understand the serial version. You already know how the matrix multiplication is done in case of serial version. And we will also see the name version of if you implementation of matrix multiplication. And we will also pinpoint some of the optimization that you can incorporate in that name version, so that the overall performance of your kernel would be faster as compared to name versions. Okay, so let us try to understand the one aspect, which is two-dimensional data space. First thing is let us consider the matrices. So in this particular collaborative, we collect matrix, consider the size of matrices as h by k. Sorry, n by k. And the resultant size is n by m. So in case of serial version of matrix multiplication, what we do is like we access the first matrix, access the column, the second matrix. Okay, and get the value. Okay, we interchange multiple elements of the row and column and add sum of all the elements in one value. Suppose this is I comma j. Suppose you want to calculate a value of I comma j in the resultant matrix. Say access ninth row from the first matrix, eighth column from the second matrix, perform kind of dot product and sum and fill in the gap over this. Okay, fill the result in I comma j, add those values and fill in those. Okay. So the one aspect that okay, this is well serial. Okay. So what I mean to say is like to calculate is in case of serial version we go something like this for every row and every column. Okay, we calculate element wise product of row and column from the two matrices and make this particular value. Suppose you want to parallelize it, you want to parallelize this particular aspect using subprogramming. What we'll do is we will launch n by n threads. Okay, so we have a result matrix C with these many number of elements n by n. Okay, so the number of threads that we are going to launch is n by n, and we will give individual thread. We will give each thread a task of accessing one row from first matrix and one column from the second matrix, perform the multiplication and addition operation, and finish this particular way. So this is a naive approach. Okay, simple approach. So where the number of threads that we are considering is n by n. Another aspect is another difference over here as compared to vector program that we are seeing is we will arrange this thread in two-dimensional space. Okay, 2D space. Okay, we will have some x and y indices for this thread. Okay, and those threads again will be grouped into blocks which are also in 2D space. Okay, so while launching a kernel, we will launch the kernel by creating two-dimensional block structure and two-dimensional two-dimensional grid structure and two-dimensional block structure. Okay, so let us first see. I will show in this particular.
I did not understand how to create a dimensional block. It also
that I will explain. So let us see this collab file. Okay, this particular cell has a CPU and GPU implementation, serial CPU implementation and naive GPU implementation. So as you can see here, CPU matrix mult, which takes two matrices. One is host A, H underscore A, H underscore B, and result is stored in H underscore result. And this M and K are the sizes of the matrices, rows, column for the three matrices, as I explained. As you can see here, there are these two outer for loops to run over rows and columns, and the inner for loops for performing the multiplication, getting the sum, and the result is stored in H underscore result, which is the result matrix. Okay. So if you consider this particular serial version, this is serial version. As I said that in case of serial version, we scan across rows and columns of both the matrices and we take this particular matrix C. Okay. Suppose you want to parallelize this particular aspect, and if I want every thread to access I row from A and J, column from B. So in that particular scenario, how that GPU version, naive GPU version will get modified. Okay. So this is a simple naive version of matrix kernel. Okay. So here, row we are first getting the indices of row and col for that particular thread. Every thread will be mapped to a particular I comma j, which is unique. Okay, so here I comma j is nothing but row and col. We are using some standard CUDA semantics to get the block dimension and thread indices over here. So since, as I said, that I'll tell you how to arrange the threads and blocks in 2D space. So we have thread idx.y to get y direction index and thread idx.x. Similarly, blocks idx.y and blocks idx.s. And here we are checking the bound. whether this row and call value which we have calculated is within the bound, and we're performing the individual element multiplication and sum operation over here. And finally, we're storing the results in D underscore C. So we can see here what we are doing is this particular GPU version give me a code which gets rid of these two for loops. Okay, so which is required in case of serial version, and every thread will perform only the access of one row and one column. Okay, so eventually giving me the results. Okay, so this is simple. This is very naive. It has some issue that I will discuss later. So let us try to understand the main code. So as you know that, okay, again, this particular flow of the main function is same as we have seen in case of vector addition program. First, we need to allocate memory at host, allocate memory in device memory. Okay, allocate memory at CPU side and GPU side. We have to initialize those matrices. Once matrices are initialized, we have to transfer data from host to device by the simple CUDA malloc function. And once the data is available in GPU memory, we will launch that particular kernel.
After the computer that features over any communication, is there any chance or possibility that it's out of the norm? It's beyond it. It's why I'm using the teams.
Yeah, there are chances. So let us say the thing is like it depends upon number of blocks and there's a okay, I will give you a simple example. I'll talk about this vector example. Okay, suppose let us say that in this vector example, we created a block with 256 threads and there are 4 blocks. Okay, so how many elements it is supposed to add? 1022. Okay. But suppose it just occurred only 1000 elements. Consider this particular case, user want to add only 1000 elements, which is not a power of like 1024. So what about in this particular scenario also, you will get 4 blocks and 256 threads, right? If you go to that particular program, so threads per block is 256 and blocks per thread is equal to n divided by threads per block. That value will become. So if you consider the block number 1, 2, 3. Okay, it is a block number 3. Not all threads will have data to operate on. Okay, some 24 element S. Okay. Last 24 threads of block number 3 don't have any work. Okay, they will remain just idle. Okay, they won't perform any addition. So this is the case in which what we are talking about that particular aspect will come into play. Okay.
It's a very simple situation. Like if you by mistake how many blocks and threads you're launching, it's not mismatching, then you will get an error and will not be able to pick up why the programs are installed. Because it's trying to access some memory that is not defined. So then you should suddenly get a segmentation fault or this kind of error to stop executing things. Unlike C, it doesn't have a very detailed compilation errors or runtime comments that come. Very difficult to pick up.
Try to understand this if condition. If I is less than num element, this is the important point that can say over here. This 24 threads will have ID, which is more than number of elements. Number of elements will be 1000. So there will be 24 additional threads. Their IDs will be 1001, 1002 to 1023. So in that case, that condition will fail. Okay. Unique thread for every thread will have a unique value of I. So in that case, those thread will remain idle, but they will not execute that addition function. Okay, so the same purpose is served over here. We calculate row and column. If this row and column values are within this bound, then only the thread will perform this particular activity. Otherwise, they will remain idle. Okay, as I said that as usual, the normal flow of the any CUDA program is like first allocate host matrices in this particular case. So we have HA, HB, HC, and HCC. So one thing you might have noticed that here for allocating a memory, we have used CUDA malloc host instead of malloc. Okay. So in earlier case, we have a malloc function. So that can be replaced with CUDA malloc host. So it has some special purpose. So it allocates pin memory. It allocates pin memory. Pin memory is a memory which cannot be swapped by operating system. Okay, it remains in the page which is allocated to those vectors or matrices will remain in the main memory. It won't be swapped by OS processes. Okay. So CUDA malloc host. And this is a piece of code which randomly initialize matrices with random numbers, random float numbers A and B. And the similar way we are allocating matrices in the device memory by using CUDA malloc. Okay, so once the matrices are allocated in device memory, we are transferring the two matrices by CUDA main copy from host to device. Okay. So the parameter is first is device pointer, second one is host pointer, third one is how much data you want to transfer, and fourth one is which direction you want to transfer the data. And as Shrijita has mentioned that whenever you use any CUDA API, it is better to check the error, okay, whether that API was successful in executing its work, so that you can okay, it should be there's some small correction over here. It should be RR is equal to this. Okay. Okay, so this is where we are creating a two-dimensional grid space. Okay, what we are doing is, if you consider the last statement, so dim3 is a keyword by which you can specify the dimension in X, Y, and Z. So the dimension of a block is block size, block size, 1. So here block size, I guess 32. So it means that we are creating every block with 32 by 32 threads. Every block will have 32 threads in X direction and Y direction 32. We are creating a grid with two-dimensional space. Okay, grid calls and grid rows. And number of columns and number of rows in grid is defined by this expression. It is somewhat same as what we have done in vector this thing, 10 divided by 256. Here the value of 256 is nothing but block underscore size, which is defined as 32. Okay. So so we have blocks in two-dimensional, and every blocks have threads which are arranged in two-dimensional. And here we are launching a kernel, that GPU kernel, GPU matrix mult, with those two dimensions and the parameters. And one more aspect that is new over here is after launching the kernel, you are calling another CUDA API, which is CUDA device synchronize. Okay. The purpose of this CUDA device synchronize is to call the host in the kernel completes the execution on GPU. One thing we need to note that kernel execution is possible with this host. See here, so this program has a piece of code. Some piece of code gets executed on host, that is CPU, and you have a kernel function which gets executed on GPU. Okay. Normally, kernel launches are asynchronous. Asynchronous means host launch the kernel and it does not wait for the kernel to finish. It will continue executing its piece of code. So we have to make the host wait till in the kernel complete the execution on GPU that can be done by this CUDA device synchronous function. So here host thread will wait till multiplication is happening. And once the multiplication gets over, your results will be in T_C matrix that we need to copy back from device memory to host memory passing CUDA mem copy. And again, we are doing CUDA device synchronize. So here it is not required. After CUDA mem copy, it is not required because CUDA mem copy API is a synchronous API. Until and unless that particular data transfer gets over, host thread gets blocked. Thereafter, we are calling our main implementation CPU matrix multiplication call, and we are just checking whether our calculation, okay, whatever results produced by GPU is equal to CPU, was in the similar kind of logic that we have seen in vector addition. And if all is okay, you are freeing the device memory and host memory. Okay. So let us check this particular program. I'm running this cell. Okay, the file is written in this particular file, matmul_c. Let us try to profile this program using nvprof. So I'm passing 3 values over here, which represent the sizes of dimensions of 2 matrices, first one and second matrix.
It's a big data. That's why it's taking that much long time. 1024 cross 1024. 2 such matrices has to be transferred from host to device and device to host. That is very too much longer time, and as well as the computation as well. So
yeah, you can see here the GPU matrix multiplication took around 6.69 milliseconds. Whereas the data transfer, right? There is that. Okay, CUDA mem copy. CUDA mem copy operation is taking around 686 microseconds. Okay. I guess it does not report the timing requirement, timing of CPU version. CPU. nvprof is like profiling only, I guess, kernel and CUDA API. Okay, one thing. There is some advanced concept where you can minimize this particular amount of time required for the execution and amount of time required for transmitting data. You can overlap the data transfer along with compute operation. Overlap these 2 operations simultaneously. It's a concept called as data string, which is the advanced concept. You can create multiple strings. And string is nothing but sequence of sequence of operation that you submit to GPU device. You can create one string which will do data transfer tasks from host to device, from device to host. Parallel along with that, you can enqueue kernel execution for another string. Okay, if the data is available, kernel can execute its operation. Kernel can execute its operation on GPU. So CUDA string is another advanced concept. Okay, so one thing that I would like to discuss is like how can you optimize this particular, or what are there any optimizations available for this name version? So first, before going to that particular aspect, please run this particular program and check whether it's running and how much time it is taking. Try to update these values. Okay, try to update a matrix size, change the matrix size to some other value and see how much time it is. Even you can change the block size value, which is declared. here hash defined block size to 32. You can update that block size to 64 and check whether you get better performance or worse performance. Or you can change it to 60 and check what kind of how much amount of time the GPU matrix multiplication is taking.
See, if you without the it's not. I don't know. So how do you when did they what's the change? It's not.
We have shared all the links in that slide. So there are 3 more collab links that if you want to explore more kind of codes, more optimizations. The codes are there, you can explore. And if you have any issues, you can contact us. So this is our so this is our lab, research lab. You can check our mail ID from here and contact if you have any problem or in the understanding. If you have some doubts, you can always contact us. And so I will just finish this session with like a small.
Subsequent sales as optimized version of management. It's called as management. You can go to that and it's a product document. It's run by our professor. It's as compared to the snare management.
It's simple, you can read it today. It's just page. I think it is that. That's what I'm trying to do.
Just take out another idea that GPU is or CUDA is not a magic wand that makes your code like da 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 and the speed up is suddenly 10%, 20 times. It's not like that. You have to identify that for specific kind of codes where there is a lot of data parallelism. Only in those cases, and it's significantly big, then only you can get a significant speed up. Like it's depending on the Amdahl's law. Amdahl's law basically defines that the portion of the code that can be enhanced, like has some speed up. The overall speed up will be like the rest of the code that is not optimized. That plus 1 by the fraction of the code that has to speed up by the speed up ratio. So that gives a total speed up. So, anyway, in CUDA, the major drawback is transferring the data from host to device. That takes a lot of time. So it's a big data points going to be like 1,000, not like that, but like 20, 22, 25, all this big data. So here GPU works like magic. Like, compared to any CPU costs, anything, you will see a significant speed up there. But in small programs, it might not be that much visible. So in some places, OpenMP will perform much better than CUDA. In some cases, CPU will perform much better, a more optimized serialized code better. In some cases, CUDA will perform significantly like magic. And so when you are trying to optimize your code or want to need a high performance computation, you have to identify the code or the algorithm that you want to improve the performance, and based on that, you have to know that which technique will actually make it better, and then find the optimization in that. So it's not that for all codes you run it on CUDA code, run it on NVIDIA CUDA, and you get a significant. It can be that its performance deteriorated compared to the CPU. That can also happen. So
how to implement the number of codes which will implement that?
So you have to understand that the GPU basically inherently do the parallelism, that it will do a lot of data parallelism. Like there's thousands of threads that can perform together. Unlike in in CPU there are many cores, multi-cores, 16 cores, 22 cores. But in case of GPU, it's in thousands, multiple thousands of cores are there. So when they are all data parallel, so there is no dependency, like it has to wait for its previous data point to finish its execution. Yes.
How will you do it? Return drive or there is some problem?
You have to understand the logic. Is it a parallel code? Like suppose you think I often use this technique. You make a box and say that any data point, identify this data point, the computation of that data point is dependent on any other data points of that place.
So that will be the bottleneck.
Yes, if there is a dependency, then there are like how much dependency is there, how much we can optimize that. Is it possible to do that in GPU? And if there is a significant dependency on its previous, last, or nearby elements, then it's might not be very useful to make a CUDA code of that. So you have to see that which realized code is there. Like in saying MBI might be a better option because it can transfer a message, it passes message transfer data across many. So that will be covered at the next stage.
Is there any analytical way that if I written the code, I know the number of variables and which library I'm using? Are there any analytical ability?
That is single instruction, multiple data. Same instruction is executed by multiple data. In that case, GPU is a better option.
So just this one, like
Yeah.
five.
Fine. And then you can like even if you are writing GPU code to get optimal one, you have to profile and check that what function takes a lot of time. What is the what?
I think you have
You have to profile what. Yeah, there is much pressure on the memory head. Then you have to check that how that memory can be used more efficiently to make it better. So there are a lot of optimization techniques that are also covered in the CPT lectures. So there are like 7-8 optimization techniques that are covered in a particular lecture. On memory side, on computation side, on G side. From all these sides, there are different optimization techniques that are covered there. You can also go there.
It's analyzing that how much memory you are.
You can do the profiling further. From the profiling, you can
Like the law is there.
so it's not generic. Like see, it's a generic architecture. So I will. So the formula is basically this. The overall speed up is basically old execution by new execution. And how do I get the overall speed up? The fraction of the 1 minus 1 that is not optimized, that part, plus the fraction of the enhanced part, that enhancement can be done by it can be done by multiprocessing, it can be done by any other technique. And which people do more processor to increase the frequency of the particle. It can be anything by the
Senior. We need a communication between CPU and GPU.
we are calling some functions.
Yeah.
So people who have joined online, it's a wrap. We have completed all the sessions.
The block size is 4.
You may leave the meeting. We are stopping our own recording.
The block size is 4. The thread size is the same. So there will be 2 blocks because you recommend allocate the 8 threads. So that's the 2 blocks parallelly simultaneously process or
Depends on the architecture. At the architecture level, how many cores?
if there's 1 4, then it goes
Suppose it is 32, then they can have now we are 32 but your one launch more than like 100,000 pieces. That becomes less on the top then we get 32.
We increase the size of the and there are many threads.
Logically, the number of blocks, but we cannot increase the number of nodes in the actual architecture.
No, I was asking like if the block size of the block is high and the codes are less. So when processing it, then it will take time to complete that code. Right? No. Yes. So